Hello all. As I wrote in one of my posts, I was busy revising a paper this past week, therefore I didn't upload. But here we are again with another past paper, and this one is Unit 5 from January 2025, and let's just dive in, all right? So, Section A, first question. A main sequence star evolves into a red giant star. Which row of the table gives the change in diameter and the change in surface temperature when the star evolves? So as we know, the diameter increases, right? Because red giant stars are larger than main sequence stars, and their surface temperature drops. So therefore, the only correct answer is C. And it's good to have the Hertzsprung-Russell diagram in mind. Okay, temperature evolves backwards, right? So red giants are up here, meaning that they have a high luminosity but very low temperature, and also they are larger. Okay, let's erase this and move on. Question 2. Ductile materials can be used in buildings to reduce the amplitude of forced oscillations during an earthquake. Which of the following is the reason that ductile materials are used? These materials are stiff. This is totally not what we want. These materials are strong. No, these materials deform elastically. This is not what we want. We actually want them to deform plastically. So the correct answer is D, and this is because we want these materials to be able to withstand an earthquake. Okay, so they will deform plastically, but the building will not collapse. Right. Okay, question 3. There is an electric field around a point charge and a gravitational field around a point mass. Which of the following is not correct? Both fields are radial, they are. Both fields can produce attractive forces, they can. Gravitational forces are only attractive for that matter. Both fields can produce repulsive forces. This is not true of gravity. It will be cool, okay? So C is the correct answer. It will be cool to have anti-gravity, but we don't, okay? So that doesn't work. D, both fields produce forces that obey an inverse square law, which is true for both. So C is the correct answer. 4, the graph shows how the binding energy per nucleon varies with the number of nucleons. The positions of 3 isotopes P, Q, and R are marked on the curve. Which row of the table lists the isotopes from least to most stable? Okay, so P has pretty much the lowest binding energy per nucleon, then comes R, right? And then comes Q. Okay, so the ordering should be PRQ. Okay, so that's option PRQ it's option B, right? So that's the correct answer. Yeah, there's nothing more to say here. So let's move on. 5, astronomers use trigonometric parallax to determine the distances to stars. Which of the following must the astronomers know? The distance between the sun and a nearby star? No, that doesn't make any sense actually. B, the diameter of the sun? Irrelevant. C, the distance between the sun and the earth. Okay, this is promising. And then D, the diameter of the earth, which is also irrelevant. So C is the correct answer, because remember, we have the sun in the center, and we have the earth now, say, and then in 6 months, right? And this is the distant star. Behind it, there are some stable stars, and you want to find the distance, right? So the angle you're measuring is this one, okay? So therefore, you need to know the distance between the sun and the earth, okay, to be able to do anything meaningful with the angle, once you determine. Okay, moving on. 6, a container is filled with a mixture of gases X and Y. The root mean square velocity of molecules in gas X is twice the root mean square velocity of molecules in gas Y. The temperature of the gas mixture is constant. What is the ratio of mass of molecules of gas X over the mass of molecules of gas Y? So let's use a clean page. So they tell us that the root mean squared, the average root mean squared velocity of gas X molecules is twice that of Y's molecules. And the temperature is the same. So let's use 1/2 m and then cx squared. And we know that from the kinetic theory of gases, this is equal to 3/2 kT. So this is mx and this is my, so 1/2 my cy squared is also 3/2 kT because they have the same temperature. Let's divide these two. KT cancels because it's the same, 1/2 cancels. And we are left with mx over my times cx squared over cy squared is equal to 1, right? So, but we know that cx squared is 2cy squared. So we have mx over my times 2, right? Because you can cancel this and replace it with a 2. This is equal to 1. Therefore, mx over my is simply 1 over 2, right? And I think this is what they ask us to find, right? Yes, the mass of molecules of gas X over the mass of molecules of gas Y. Therefore, the correct answer is C. Question 7. The value of the Hubble constant h0 was initially estimated to be 1.5 times 10 to the negative 17 seconds to the minus 1. By the way, never confuse seconds to the minus 1 as used in the Hubble constant with hertz. This is not a frequency, okay? Now, using this initial value, the age of the universe is t. Now, scientists estimate that h0 is actually 2.1 times 10 to the negative 18 seconds to the minus 1. Which of the following is the age of the universe using this value of h0? Okay, so we can find the initial age of the universe. So let's call it t initial, okay? And it's not sorry, I called it initial just to distinguish between the two. Maybe it's better to call it t1, okay? It's better. So t1 is 1 over h0, right? So it's 1 over 1.5 times 10 to the negative 17, and this is in seconds. And if we carry calculation, we'll find 6.67 times 10 to the 16 seconds. Okay, so this is the age of the universe as determined using this Hubble constant. Now with the new Hubble constant, let's do T2 is 1 over h0, let's call it subscript 2, and maybe call this subscript 1. So this is 1 over 2.1 times 10 to the negative 18, and then this is in seconds. And if we do this calculation, we will find 4.76 times 10 to the 17 seconds. So if we divide t1 over t2, we will find 7.14. Therefore, t2 over t1 is that. So t2 over t1 is 7.14. Therefore, t2 is about 7.1 t. Actually, I'm sorry for creating this confusion, but this should be t because this is what they say in the wording of the problem, that t is the age of the universe as estimated using this constant, right? Therefore, also let's erase that subscript. So this is the new estimation, okay? So 7 times older, pretty much, okay? So the correct answer is D. All right, question 8. A pendulum is made by attaching a light paper cone to a thin string as shown. The pendulum is displaced and set into oscillation. Plasticine is then added to the paper cone to increase the mass of the pendulum. The pendulum is set into oscillation again. Which of the following is correct for the paper cone with plasticine? The frequency of oscillation has increased. And then the second argument, the second option is the period of oscillation has decreased. But recall that for a pendulum, the period is given by 2 pi, the square root of the length of the string over g. So there is no mass dependence, so A and B are automatically wrong, right? So let's examine the other two options. The amplitude of oscillation decreased more quickly. Why would that happen? It doesn't make sense. But D says the amplitude of oscillation decreased more slowly. And actually, that's the correct answer, okay? And the reason is that, so D is the correct answer. The reason why C is not correct is that the reason why, so damping, let's write it down, damping is due to air resistance, right? Therefore, if we increase the mass, the air resistance, the same air resistance is now acting on a heavier mass. Therefore, the effect is not as big as with the lighter mass. So the best way to convince you is think of a rock. If I throw a rock from a building or a coin, because it has mass, it falls fast. If I throw a feather, it falls slower, right? And this is due to air resistance acting on the lighter mass, because in a vacuum they will both arrive at the Earth at the same time, right? So it's the same effect here. Air resistance is there. If we increase the mass, the effect of the force is smaller. Therefore, the amplitude decreases, slowly. Okay. I hope this makes sense. If it doesn't, ask me in the questions, in the comments, and I will clarify. And also, please subscribe. I never say that, but yeah, I mean, it's good to have subscribers. So, question 9. Due to tidal action, the moon is slowly moving away from the Earth. As the moon moves away from the Earth, the gravitational force between the Earth and the moon changes. The gravitational potential energy of the moon also changes. Which of the table correctly shows these changes? Okay, so let us write down the formulas actually. So the gravitational force between the Earth and the moon is G times the mass of the Earth times the mass of the moon over r squared, right? And then the gravitational potential energy is equal to the mass, of the moon times times the gravitational potential of the Earth. Excuse me for hesitating. Okay, so this is equal to minus G times the mass of the Earth times the mass of the moon over r. Okay, now they say that the moon is moving away. So if r increases, then we immediately see that the force decreases because we have the 1 over r squared dependence. But if r increases, the gravitational potential energy increases, right? And this is because this becomes less negative, if that makes sense. So if you compare, for example, the number minus 1 over 10, assuming that the radius is 10, say, so minus 1 over 10 is actually larger than minus 1 over 2, okay? So if the radius is 2, okay? And this is because if you draw the line axis, the number axis, minus 1 over 10 is here, and say minus 1 over 2 is there. So minus 1 over 10 is actually larger, so the gravitational potential energy increases, and therefore the correct answer is B, okay? So be careful with the negative sign of the gravitational potential, okay? Because it comes with a negative sign. Okay, question 10. Energy is supplied at a constant rate to a material. The material is initially solid. As energy is supplied, the solid melts to form a liquid, and finally the liquid turns into a gas. The mass remains constant during the heating process. The graph shows how the temperature changed with time. Okay. Which of the following is correct? Okay, the specific heat capacity of solid is larger than the specific heat capacity of liquid. Okay, so this is a question that concerns the gradients that we see here. So let's go write a few things down to help us. So the energy in the parts of this graph where the material actually increases, its temperature, but it's within the same state. Okay, so for example, here the temperature increases, but the material is solid. Here the temperature increases, and the material is a gas. So this increase is given by Cm times the change in temperature. Okay, but here we have the temperature plotted against time. So to make sense of that, recall that power is energy over time, right? So energy is power times time. And assuming that we use a heating device of constant power, we can cast this into an equation that looks like this. Delta theta is equal to P over M times C times time. Okay, so this is a linear graph with a gradient. So the gradient is proportional, because we don't care about the equality. The gradient is proportional to 1 over C. Okay, so the steeper the gradient, the less the specific heat capacity. I hope this makes sense. Therefore, A is automatically wrong. Specific heat capacity of solid is this one. So A says the specific heat capacity of solid is larger than the specific heat capacity of liquid. So this is actually in reverse. Then B says the specific heat capacity of solid is larger than the specific heat capacity of gas, but we see that they are the same, really. Okay. Then C, the specific heat capacity of solid is equal to the specific heat capacity of liquid. This is not true, right? And D says that the specific heat capacity of the solid is equal to the specific heat capacity of the gas, which is true, right? Because you can see it that this gradient and this gradient are the same. So D is the correct answer. Okay, I hope this makes sense. We just introduced the concept of a heater heating this material pretty much, okay? Okay, section B, question 11. We see that this is a 3-mark question. And as I say in almost all of my videos, this should take about 3 minutes, okay? So 1 minute per mark is time you should devote more or less to a problem, okay? A mass of 0.35 kilograms is hung from a spring. The mass is displaced vertically from its equilibrium position and released. The mass oscillates vertically with simple harmonic motion with a period of 0.95 seconds. An extra mass is added and the period increases to 1.15 seconds. Calculate the added mass. Okay, so we know that the period for an oscillating mass on a spring is 2 pi times the square root of m over k, right? So we can use this twice, okay? The first time we will use it with the mass hung from the spring and oscillating with a period of 0.95 seconds. And this will give us k because we are not given k, right? So let's plug things in. So 0.95 seconds is equal to 2 pi times the square root of m. Sorry, we said we're going to replace m. So 0.35 over k. Okay. So if we square both sides, we will find 4 pi squared times 0.35 over k. Therefore, k is equal to 15.3 newtons over meters. And now let's apply it one more time. So t, let's call it t prime, is equal again to the same formula, but now we are adding an extra mass, okay? and the period increases to 1.15 seconds. So how can we write this mathematically? So this is equal to 2 pi times the square root of m plus the added mass, which we call m prime, over k. Okay, and the only unknown now is m prime, so we can take the square again. So t prime squared is 4 pi squared times m plus m prime over k. Therefore, m plus m prime is t prime k over 4 pi squared. And now we can write this as this is squared, I'm sorry, t prime squared times k over 4 pi squared minus m. And if we plug in numbers, we will find 0.16 kilograms, which is the answer. Okay, I hope this makes sense. Question 12. The graph shows how gravitational potential V varies with distance r from the center of the Earth. Show that the mass of the Earth is about 6 times 10 to the 24 kilograms. By the way, this is an example of what I was talking about earlier. See how when the distance increases, the gravitational potential actually increases in the sense that it becomes less negative. Okay, what I'm talking about is that at the distance of 0.1 times 10 to the 8 meters from the center of the Earth, the gravitational potential is minus 4 times 10 to the 7 joules per kilogram. But at the radius of the Earth, at a distance of 1 times 10 to the 8, it becomes about minus 0.4 times 10 to the 7. So it increases, okay? But this is not what we care about in this problem. We actually care about finding the mass. So recall that V is minus G times M over R. So M is minus V times R over G. So we can choose any point we want on this graph and read the values and put them into that equation. So I chose this point over here. So if R is 0.2 times 10 to the 8 meters, V is minus 2 times 10 to the 7 joules per kilogram. Okay, so if we plug in this value, we have M is equal to minus 2 times 10 to the 7, right? And then this is joules per kilogram. Whenever I plug in numbers, I put the numbers to the left and I put all the units to the right. This is a technique I like to follow. Okay, so, and then R is 0.2 times 10 to the 8, and this is meters. And then in the denominator, we have 6.67 times 10 to the negative 11. And the gravitational constant is given in units of newtons times meters squared over kilograms squared. So these kilograms cancel. And this yields 5.99 times 10 to the 24 kilograms, okay? And this is because newtons times meters make joules, so these meters cancels actually, okay? Now newtons times meters is 1 joule, so joules cancel, and we are left with kilograms, and we can also write this as 6 times 10 to the 24 kilograms. Okay, question 13. A pan of water is heated on a hot plate as shown. A mass of 0.65 kilograms of water is boiled away in a time of 1,250 seconds. The power of the hot plate is 1800 watts. Calculate the efficiency of the boiling process. And they give you the specific latent heat of vaporization for water as 2.26 times 10 to the 6 joules per kilogram. Okay, so the first step is to find the energy needed to boil this. So this will be the mass of the liquid times the latent heat. So 0.65 kilograms times 2.26 times 10 to the 6, which yields 1,469,000 joules. And then the second step is to find how much energy the hot plate gave us. So the energy of the hot plate, this is supposed to be a subscript. I'm sorry if it looks funny. So the hot plate has a power of 1800 watts, and 1 watt is 1 joule per second. And it's heated for 1250 seconds. So you multiply by that to uncover how much energy the hot plate gives in that time, which is 2,250,000 joules. Okay, and then we have to recall that the efficiency is equal to the useful energy, so E useful, right, over the energy provided in the input. Okay, in this case, the useful is the one we actually use to boil, so 1,469,000 over the energy provided by the hot plate, which was the input in this case, so 2,250,000. These zeros cancel, and if we use a calculator, we find 0.6053, which is 65.3%. Okay, I hope this makes sense. Question B, putting a lid on a boiling pan reduces the energy transfer needed from the hot plate to keep the water boiling. Explain why. Okay, so obviously the steam doesn't escape now. Doesn't escape, or a very small amount escapes. Okay, so very small amount escapes. Okay, and therefore, the energy transfer is more efficient because, and also because heat is not lost to the environment just by using the lid. Okay, question 14. The Earth takes 365 days to make one complete orbit of the Sun. Show that the mass of the Sun is about 2 times 10 to the 30 kilograms. They give you the radius of the Earth's orbit about the Sun, and they give you 1 year in seconds. So how are you going to think about this? So in this kind of problems, you usually have to write down that the gravitational force is what provides the centripetal force needed for the system to stay in orbit, right? So we have G times the mass of the Sun times the mass of the Earth over R squared is equal to the centripetal force, which is M omega squared times R, okay? And this should be the mass of the Earth, which cancels. So in this case, we solve for the mass of the Sun, which is equal to 4 pi squared R to the cubed. Let me write this again, squared R to the cubed over the period squared times G. Okay, so let's use a clean page to write down the numbers. So this is 4 pi squared times 1.49 times 10 to the 11 cubed over 6.67 times 10 to the negative 11 times 3.15 times 10 to the 7 squared, which is the period squared. And we find 1.97 times 10 to the 30th kilograms, or 2 times 10 to the 30 kilograms. So we see that it's about 1 million times heavier than the Earth. Okay, part B. A television program claimed that the gravitational field strength at the surface of the Sun is 28 times the gravitational field strength at the surface of the Earth. Deduce whether this claim is correct, and they give you the diameter of the Sun as 1.39 times 10 to the 9. So the gravitational field strength is equal to the gravitational constant times the mass of the sun over the radius of the sun squared. Okay, so this is 6.67 times 10 to the negative 11 times the mass we just found, 1.97 times 10 to the 30th, okay, over the radius squared. The radius is half the diameter, so 0.695 times 10 to the 9 squared, and this yields 272.03 newtons per kilogram, which is about 20, if we divide by 9.81 newtons per kilogram, which is G at the surface of the Earth, this is 27.73, which is about 28. So the claim is correct. Okay. Question 25 is a long writing problem that awards 6 marks. And in this kind of problems, you have to provide about 6 statements that support an argument that they ask you about. Okay, so about 6 sentences, in other words. Okay, so the Millennium Bridge, as shown, is a suspension bridge for people to cross the River Thames in London. Sadly, I've never been to London. If you've been, write in the comments. So let's move on. The bridge developed a large swaying motion when people walked across. Dampers were fitted to the bridge to correct the swaying motion. Explain the cause of the large swaying motion and the effect of the dampers. So as people walk, they create a force, right? This is the driving force. So as people walk, they apply a driving force to the bridge. If the driving frequency from their footsteps, it's better, okay, from their footsteps matches the natural frequency of the bridge, resonance occurs. Okay, the other point you can write is that at resonance energy, at resonance energy, at resonance, now at resonance, energy is transferred to the bridge very efficiently. Okay, the amplitude of the bridge's motion becomes maximum, I mean, it increases, right? So the amplitude of the bridge's oscillation increases and the swaying becomes large. Okay, the dampers remove energy from the bridge And this dissipates the energy, okay, and it reduces the amplitude of the oscillation. So this dissipates the energy and reduces the amplitude of the oscillation. Okay, and this was number 15. I hope it makes sense. Okay, number 16 was probably my most favorite problem in this test because if I recall correctly, you have to go to my video on Cepheid stars and luminosities and how to determine the distance from stars and such. And I came up with an example of my own to explain how to use Cepheid stars, okay? And this is exactly the example I came up with. Okay, so I promise I came up with the example I show in my past video alone before seeing this, but this is exactly what I was talking about. So 16. Cepheid variable stars are used by astronomers, excuse me, as standard candles. State what is meant by a standard candle. So this is a star of known luminosity. Okay. B. The luminosity of Cepheid variable stars varies periodically. There is a linear relationship between the period and the mean luminosity of a Cepheid variable star as shown. So basically, as the period increases, the luminosity increases, as we see in this graph. And this is the mean luminosity over the luminosity of the sun in the vertical axis, in the y-axis, okay? And period is in the x-axis. Okay, I, the variation in luminosity L of this Cepheid variable star with time t is shown below, and we see this nice periodical graph show that the mean luminosity of this Cepheid variable star is about 8 times 10 to the 29 watts, and they give you the luminosity of the sun, which we need. I mean, because they give us the mean luminosity over the luminosity of the sun. Okay, so the first step is to find the period, right? So choose any two of the following. So you can choose this point and this point, for example, and we see that the period is about 5 days, right? It goes from 2 to about 7. And you can see the same if you choose the peak. You can also choose 2 peaks. And again, this is the period, and you can read it off the axis. This is about 3 days, and this is about 7, something like that. So 9 or 8, something like that. So I deduce the period to be about 5 days, okay, from this graph, and I use these 2 points down there, okay. So I assume that this is 7, this point there is 7. So I assume that the period is 5 days. Okay, you can check for yourselves. I mean, they give you a range. You can say, oh, it's 5.2 days, for example, etc. But anyway, using the period as 5 days, we have to then go to the other graph and find where the 5 days are. So this is a log plot. So to read it, you start with 1, this is 2, now this is 3, 4, 5, 6, 7, 8, 9, and 10. So 5 is this point over here, which corresponds to this point, and we read that the luminosity is 2000 times the luminosity of the sun. Okay, so the luminosity when the period is 5 days is equal to 2000 times the luminosity of the sun, which is 2000 times this luminosity, 3.83 times 10 to the 26 watts, and the calculation yields 7.66 times 10 to the 29 watts, which is about 8 times 10 to the 29 watts, which, I mean, arguably, if you use 5.2 days, maybe you will get closer to 8, but okay, this is good enough. I hope the method is the most important, right? We find the period from the luminosity versus time graph for Cepheids, okay? And then we use the luminosity over the period to find the luminosity of the Cepheid and do the calculations and so on. Okay, question 2. When viewed from Earth, the mean intensity of this Cepheid variable star is 5.1 times 10 to the negative 4 watts per square meter. Determine the distance of this Cepheid variable star from Earth. Okay, so the intensity is given by the luminosity over 4 pi and then the distance squared, okay? Because we imagine that this radiation is spread over the surface area of some sphere, okay? And the surface area of a sphere is 4 pi d squared, okay? So d is the square root of the luminosity over 4 pi times the intensity, okay? So if we plug in the numbers they give us, and the number we calculated, okay, the luminosity was calculated to be 7.66 times 10 to the 29, and then we have 4 pi, and then I is 5.1 times 10 to the negative 4, and the units are under the square root, okay? The units for luminosity are watts, and for intensity is watts per square meter. So watts cancel, and we get 1.09 times 10 to the 16 meters, which is about 1.1 times 10 to the 16 meters, quite far away, okay? I enjoyed this problem because I think it's the first time I saw a problem related to Cepheid stars, which are cool to study, etc. So anyway, question 17. The graph shows how the acceleration a of an object varies with the displacement x of the object from its equilibrium position. Question A, explain how the graph shows that the mass is moving with simple harmonic motion. Okay, so we see immediately that this graph has a negative gradient, right? So the graph has a negative gradient. Okay, so the acceleration is proportional to minus x, okay? And therefore, acceleration is proportional to x, and in the opposite direction, okay, it passes through the origin, okay, so a is equal to minus omega squared times x. So this is a plot that shows acceleration. What was the question again? It's a graph that shows simple harmonic motion, okay? So I hope this is clear. I mean, it's kind of solving itself just by looking at the graph, okay? But you can write a few arguments. It's a 2-mark problem, so 2 talking points are enough. All right, B, part I, calculate the maximum kinetic energy of the object, and the mass of the object is given as 0.25 kilograms. Okay, so first of all, we need to find the velocity, right? The velocity is omega times amplitude, right? Now, what is the amplitude? We can go to the graph and see that the extreme values here are these two. So the object goes from minus 0.04 to 0.04. Therefore, the amplitude is simply 0.04 from the graph. So the amplitude is 0.04 meters from the graph. Okay, now the gradient will give us minus omega squared. Let's find the gradient. So to make my life easier, I use these points over here, okay, and the origin, okay. So you have to divide this by this, okay. So we have the acceleration over here is 0.7. For this point, that's 0.7, okay. 0.7 minus 0, because at the origin we have 0 acceleration, okay. And the amplitude is minus 0.04 minus 0, so minus 0.04 minus 0, okay. So minus 17.5 is the gradient, which is equal to minus omega squared. Therefore, omega is 4.18 radians per second. I will need a clean page. So the energy, they ask for the maximum kinetic energy of the object. So this is equal to 1/2 mv max squared, which is equal to 1/2 m omega squared a squared, which is equal to 1/2 times 0.25 times the omega we just calculated, 4.18 squared, times 0.04 squared, which yields 3.5 times 10 to the negative 3 joules, which is the answer. And actually, this is the maximum potential energy as well, because these two interchange in simple harmonic motion. Okay, but they don't ask about that, so we don't care. Okay, part 2. Sketch a graph on the axis below to show how the kinetic energy of the object varies with displacement x. You do not need to do any more calculations. Okay, so first of all, this is the displacement, right? So when think of a pendulum, right? So at the maximum displacement, both left and right, okay, the speed is 0, therefore the kinetic energy is 0, right? The maximum velocity is in the middle, right, at the equilibrium position. So that's the maximum. So you can connect these 3 points. And this is what the kinetic energy looks like in simple harmonic motion. Same applies for an oscillator, by the way, okay? So this was question, what was it, 17. Okay, question 18. The diagram shows dark lines in the continuous spectrum of electromagnetic radiation from the sun. Atoms in the outer regions of the sun absorb electromagnetic radiation. This produces the dark lines in the spectrum. Explain why electromagnetic radiation is only absorbed at some wavelengths. Okay, so first of all, in the sun we have gases and plasma. I mean, it's a plasma really, but you can think of a gas as well. I mean, kind of a gaseous plasma mixture. Okay, so the first thing we can write here is that atoms in gases, in gases or plasmas, okay, have discrete energy levels. Okay, photons are absorbed only when their energy matches the energy difference between atomic levels. Oops. Atomic levels. Okay. Hence, those photons will be missing from the spectrum because they were absorbed and then re-emitted at some other point, but in general they are missing, and they create the dark lines because these lines are absorbed by the gases in the outer layers of the sun. Okay, moving on to question B. The sun rotates on its axis. The diagram shows the sun rotating at its equator. Okay. One of the dark lines in the spectrum occurs at a wavelength of 589 nanometers. Radiation is received on Earth from opposite ends of the sun's diameter. There is a difference between the wavelengths of radiation received from opposite ends due to the sun rotating about its axis. The difference in wavelengths is 7.94 times 10 to the negative 3 nanometers. A website states that at its equator, the sun rotates once every 27 days about its axis. Assess the accuracy of this statement, and they give you the radius of the sun and 1 day in seconds. Okay, so the first step here is to find the Doppler factor. Okay, so delta lambda over lambda is equal to V over C. Okay, so V is C times delta lambda over lambda. Okay, but now we have to also divide by 2. Okay, this is the trick here, and this is because the difference in wavelengths is given as this value over here, 7.94 times 10 to the negative 3 nanometers. But really there are two wavelength differences. One from the one end of the sun, which is going to be a little bit down because the one end of the sun is moving away from us, and the other end of the sun, when I say end, I mean the diameter, so these 2 points. So you will have 2 delta lambdas, if that makes sense. This one will be a little bit up because, down because it moves away from us, right? So this end, as we observe the sun, this end, the right end, because it rotates this way, it's moving away from us, so it's red shifted, whereas this end is moving towards us, so delta lambda increases. I mean, it's blue shifted. Okay, so this delta lambda, so what I'm trying to say is that we need to take the average of that value. Okay, I hope that makes sense. Okay, so if we take the average, because this is the difference, I mean, from the two sides. Okay, so we have to average. So if we plug in values, we will find 7.94 times 10 to the negative 3 times 3 times 10 to the 8 over 2 times 589, which is the original wavelength. This will give us 2022.1 meters per second, okay, for the velocity of rotation. But if we use V equals to omega times the radius of the sun, and they give us the period, which is 27 days, right? So if we use this formula to find the velocity of the sun, we will find that V is 2 pi over the period times the radius of the sun. So this is equal to 2 pi times the radius of the sun, which is 6.96 times 10 to the 8 over the period, which is 27 days, times 8.64 times 10 to the 4 seconds for 1 day. This yields 1,874.6 meters per second. So there is a mismatch. So mismatches the other calculation. Okay. And what was the question again? So assess the accuracy of this statement. So it's inaccurate, okay? But close. I mean, if you look at the numbers, it's kind of close, but not accurate. Okay. Question 19. A filament bulb contains argon gas to extend the lifetime of the filament. while the bulb is off, the argon gas inside the bulb is at a temperature of 290 Kelvin. The pressure of the argon gas inside the bulb is 75% of atmospheric pressure. The volume of the bulb is 1.25 times 10 to the negative 4 cubic meters, and the atmospheric pressure is 1.03 times 10 to the 5 pascals. Calculate the number of argon atoms in the bulb. Okay, so we can use PV equals nkt for ideal gases. So N is P times V over kT. So this is equal to 1.03 times 10 to the 5 times 1.25 times 10 to the negative 4 over 1.38 times 10 to the negative 23, and then 290 kelvins. And if we carry the calculation, we will find 2.41 times 10 to the 21 atoms. Okay. Question B. While the bulb is on, the pressure of the argon gas is 83% of atmospheric pressure. The manufacturer states that the temperature of the gas inside the bulb is about 60 degrees Celsius while the bulb is on. Assess whether this statement is accurate. Okay, so initially we have the initial pressure P1 times V is equal to Nk times T1. And then this is when the bulb is off. When it's on, we have P2 times V. It's the same volume, right? It doesn't change. And then it's the same N, the same number of atoms. They don't escape, right? So this is equal to Nk, and now T2. Okay, so we can divide these two. K and N cancels, V cancels, and so P1 over P2 is T1 over T2. And we are interested in T2, right? So T2 is P2 over P1 times T1. So we have 0.83 times the atmospheric pressure. And then initially it was 0.75 times the atmospheric pressure. And the initial temperature was 290. So this yields 320.9 degrees Celsius, which is about 48 degrees Celsius. So the statement is inaccurate. So inaccurate statement. All right. Question C. While the bulb is on, radiation is emitted by the filament. The radiation has a peak power output at a wavelength lambda max of 1100 nanometers. Calculate the power output of the bulb, and they give you the surface area of the filament. Okay, so we will use Wien's law. Lambda times T is 2.898 times 10 to the negative 3. So T is 2.898 times 10 to the negative 3 over the wavelength, which is 1100 times 10 to the negative 9. So this yields the temperature of 26,345 Kelvin. Okay, and then we can use Stefan Boltzmann's law to calculate the luminosity. So L is sigma times the surface area times T to the 4th. So 5.67 times 10 to the negative 8 times the surface area, which is 1.55 times 10 to the negative 5 square meters, times the temperature to the 4th, 26,345 to the 4th, and this yields 42.3 watts, which is the typical wattage of a light bulb. I mean, if you ever guys went to a supermarket and bought one of those old filament light bulbs, they are usually 50 watts, maybe 100 watts, something like that. Okay, question 2, part 2, excuse me. Suggest why the actual power output of the bulb may be lower than the value calculated. Okay, so nothing is a perfect black body radiator, so not a perfect black body radiator. Okay, and some energy might be absorbed by the glass. All right, question 20. I found this a strange problem, okay, and you will see why. So 50 years ago, Henry Petrie developed a device for the kitchen that produces instant boiling water. A modern version is shown. There's a tub, a tank. Okay, the system consists of a small tank connected to the water supply. Water in the tank is heated under pressure to a temperature of 110 degrees Celsius. When the water flows out of the tub, the temperature falls to 100 degrees Celsius. Okay, question A. Water enters the tank at a temperature of 12 degrees Celsius. An electrical heater increases the temperature of the water to 110 degrees Celsius. The water does not boil because it is under pressure. Calculate the time taken to heat a full tank of water to 110 degrees Celsius. And they give you the potential difference across the heater, the current in the heater, the volume of the tank, the density of water, and the specific heat capacity of water. Okay, first step is to find the power of this heater. Okay, so power is just current times voltage, right? So 12.6 times 230 yields 2,898 watts. Okay, and now the second step is to use this power. So power is energy per time, right? So time is energy over power, where power is the power I just calculated, and the energy to heat this water is going to be equal to the specific heat capacity of water times its mass times the temperature change over the power. But they don't give us the mass, so we have to find it by multiplying the density of water times the volume of the tank, right? Times delta theta over P. All right, I'm gonna use a clean page. So if we plug in all the numbers, so C is 4,180 times the volume 3 times 10 to the negative 3 times density 997 times the temperature change, which is 98 because you go from 12 to 110. And temperature differences, in general, we have to use temperature in Kelvin, but because the temperature difference, the same temperature difference in Celsius is the same as the temperature difference in Kelvin, okay? And we divide with the power, which is 2,898 watts, which we calculated, and this will yield 422.8 seconds, which is about 7.05 minutes. Okay, and yes, we have to move on. Part B, the average rate of energy transfer from the tank to the surroundings is 9.5 watts, excuse me. A full kettle contains 1.4 times 10 to the negative 3 cubic meters of water. It takes 180 seconds to bring a full kettle of water to 100 degrees Celsius. The kettle is used to bring enough water for 28 cups of tea to 100 degrees Celsius. A reviewer compared the energy transfer from the tank to the surroundings in 24 hours with the energy transferred by the kettle to make the tea. The reviewer claimed that the energy transfer from the tank would be greater than the energy transferred by the kettle. Assess the validity of the claim. And the power of the kettle is 2,600 watts. The volume of water in 1 cup of tea is 3.5 times 10 to the negative 4 cubic meters. Okay, this is a lot. This is a lot. I mean, it's information. So first of all, let's start with the volume of the kettle over the volume of 1 cup. Okay, so this is going to be 1.4 times 10 to the negative 3, okay, cubic meters. Sometimes I forget to include the units, over 3.5 times 10 to the negative 4 cubic meters. Okay, and this is 4 cups. Okay, so a kettle can serve 4 cups. Okay, so we need 4 cups. So we need 7 kettles for 28 cups. Okay, now using 7 kettles, we will need, so 7 kettles times, where was it? Times the power of 1 kettle, which is 2600 watts, right? And we need to boil it for 180 seconds, okay? So, by the way, watts is joules per second, and then 180 seconds makes the seconds go away, okay? And if we multiply this, we see that this needs 3.28 times 10 to the 6 joules. I hope this makes sense. Now, this was a kettle. For the average rate of energy transfer from the tank to the surroundings, okay, we will use a different reasoning, okay, for this piece of information. Okay, so in one day, 9.5 watts are lost. So 9.5, let's use it, let's say joules per second, which is 1 watt, okay? But then in one day, so one day has 24 hours, an hour has 60 minutes, and a minute has 60 seconds, okay? So the seconds again go away. And if we do this multiplication, we see that in a day we lose 820,800 joules, which is of course less than 3.28 times 10 to the 6 joules. So this claim is false. So, okay, claim is false. Okay, now question 21. Promethium is produced as a byproduct of nuclear fission. An isotope of promethium, PM147, decays by beta emission. The thickness of paper produced in a paper mill can be monitored using beta radiation as shown. The count rate recorded by the GM tube, the Geiger-Müller tube, is a measure of the thickness of the paper. Explaining why a source of beta radiation is suitable to monitor the thickness of the paper. So beta particles can actually penetrate paper, unlike alpha particles that are blocked, okay? So beta particles can penetrate paper, okay? And the count rate after, actually, I'm not going to write it in parentheses because it's important. So the count rate after they go through the paper, okay, depends on the thickness of the paper. Excuse me. On the thickness of the paper. And this is the full answer, okay? I hope this makes sense. In areas where the paper is thicker, you will have less, a reduced count rate compared to areas of the paper that are thinner, okay? Right. B, promethium 147 decays by beta decay to an isotope of samarium Sm. Complete the decay equation. Okay, let's start with the beta particle. It has 0 mass number and a -1 charge number, and therefore samarium is 147, right? Beta decay never changes the mass number, okay? but it in the case of a beta minus decay like here, it increases the atomic number by 1, and if it's a beta plus decay, it reduces the atomic number by 1. Okay, so here it's 62, because we have 62 minus 1 equals to 61, and we have 147, so the right hand side matches the left hand side. All right, part 3. In a particular paper mill, the PM source was replaced when the activity of the source had decreased to 0.75% of its initial activity. Calculate the time that the source had been in use, and they give you the half-life of promethium-147 as 2.62 years. Okay, we will use the fact that the activity follows the radiation decay law, e to the minus lambda t. Lambda can be calculated using ln of 2 over the half-life, t1 half, I'm sorry. Okay, so this is just 0.26 years to the minus 1. And if we go back to the nuclear decay equation and write it as A over A naught is e to the minus lambda t. And then A over A naught is 0.75%, so 0.75 over 100. And this is equal to e to the minus 0.26 times t. Okay, therefore, minus 0.26 times t, if we take the ln in both sides, is equal to minus 4.89. Therefore, t is 18.8 years. Quite a lot of time. Okay. 18 years ago, okay, this is nearly 19 years ago, I was a college student. It's been a while. Okay. Part B, the most stable isotope of promethium is PM145. Calculate the binding energy per nucleon for nucleons in a nucleus of promethium-145. Give your answer in MeVs. They give you the mass of a promethium-145 nucleus in S144.913 U's, atomic mass units, and the neutron mass is 1.00867 atomic mass units. All right, so the binding energy, this is where we will start, is Z times the mass of the proton plus N times the mass of the neutrons minus the mass of promethium in this case, okay, times C squared. All right, so let's write down numbers. The Z for promethium is 61. How do we know? From here, right? So 61 times the mass of the proton, which is 1.67 times 10 to the negative 27 kilograms, plus N, since it's promethium 145, we need 84, because 84 plus 61 is 145. So 84 times 1.00867, and then one atomic mass unit is 1.66 times 10 to the minus 27 kilograms, minus the mass of promethium, which is 144.913 times 1.66 times 10 to the negative 27 kilograms. And then we have to multiply by 3 times 10 to the 8 squared. And this yields 1.77 times 10 to the negative 10 joules. And if we divide by 1.6 times 10 to the negative 19, we will find the same energy in electron volts. So 1.1 times 10 to the negative 9, times 10 to the negative 9 electron volts. Okay, so this is the binding energy. Now the binding energy per nucleon is this quantity we just calculated, 1.9 times 10 to the 9 electron volts, which you can write actually, let me think. No, let's keep it like that. So over 145, which is the mass number. So this yields 7.62 times 10 to the 6 electron volts per nucleon, which is 7.62 MeVs per nucleon. So this value of the binding energy per nucleon is always close to 8. Okay, that's the number that's a number to remember. And I say this because I studied nuclear physics. So for any isotope in nature, the binding energy per nucleon will be from about 1 for deuterium. So it's between 1 and say 8.5. Okay, so if you find something very large or very small, you made a mistake, check your calculation. All right, this was Unit 5 from January 2025. I plan to make more videos, but I started having a few projects that take away time. So yeah, we'll see. But thank you guys for those of you who like the videos, who subscribe, and those of you who ask questions in the comments. It means a lot to me. Hopefully I will keep pumping this out. See you in the next video, guys. Please subscribe. Bye.